I'm Takahiro Ueda, a JSPS Overseas Fellow at the Center for Astrophysics. So I'm going to talk about the planet formation within the inner region of thermally evolving disks. By the way, so this movie is taken last weekend at the Santa Barbara Stearns Wharf, where I found a sea lion playing with a group of the small fishes. So this is actually my first time to see wild sea lion. So if you have never saw them, so I highly recommend to visit there. Okay, so let's start to about the demographics of the exoplanetary systems. So this figure shows the planetary mass versus orbital period of the detected exoplanetary systems along with the inner solar systems. And you can see that there is a lot of close-in super-Earths, which is much more massive than the inner solar system planet. And their typical orbital period is roughly 10 days, and which correspond to the major axis of roughly 0.1 AU. But in contrast, the inner solar system planet has a relatively small mass, and the orbital period is roughly 1 AU. So there is a kind of two distinct populations in the observed planetary systems. Of course, these small planets, it's very difficult to detect, to be detected. So we are not sure that these exoplanetary systems are more like a continuous distribution of two distinct planetary populations. But anyway, there is a clear difference in these two planetary systems. And if we look at the more detailed orbital architecture of exoplanetary systems, we can see that there is a kind of excess in the first order resonances. For example, 2-to-1 resonances and 3-to-2 resonances. So this is a kind of indication that there was a convergent inward migration in the two planetary planets. So they are trapped into the mean motion resonances, and after the gravitational interaction, these planets are ejected from the resonances. But if we look at the inner solar system, there is no clear resonance configuration. So the very fundamental question is that do exoplanetary systems and the inner solar system form in similar ways, or completely different mechanisms? So that is a kind of fundamental question in the planet formation. So in this talk, I'd like to focus on the planet formation at the dead zone inner edge, where the temperature reaches roughly 1000 Kelvin, above which the thermal ionization of the gas disk is enough to activate the magnetorotational instability. So why we focus on this region? That because one reason is very simple, that this location is typically located at the, let's say, 0.1 AU, which is similar to the typical orbital semi-major axis of the exoplanetary systems. And within dead zone inner edge, the temperature is enough high to activate MRI, so the turbulence strength is very high. But on the other hand, outside the dead zone inner edge, the MRI is inactive because of the low ionization degree, so that there is a pressure bump just outside the dead zone inner edge. And if there is a pressure bump, the dust particle drifting from the outer region can be trapped. So then this dust trap can form planetesimals, roughly at 0.1 AU. So, but if we consider the disk evolution, dead zone inner edge can be located much further from the central star. So this figure shows that the mid-plane temperature as a function of the radial distance, and the different lines correspond to the different mass accretion rate onto the central star. If we look at the later stage of disk evolution, let's say the accretion rate of 10 to the minus 9 solar mass per year, the dead zone inner edge is roughly 0.1 AU here. But if the accretion rate is high, so 10 to the minus 7 solar mass per year, then dead zone inner edge can be located around 1 AU. So how does the thermal evolution of the innermost region affect inner planet formation? So this is a question I want to answer in this talk. So this is an example of the dust evolution in such early disk evolution phase. And we consider, in this simulation, we consider the magnetically evolving protoplanetary disk. So in this simulation, we show the mid-plane temperature here, and the gas surface density here, and the dust surface density in the right panel. And we assume that the initial condition, initial disk mass of 0.1 solar mass per year, 0.1 solar mass, and the disk size of 15 AU. And we assume that the disk evolves with the MHD disk wind. And we assume some kind of alpha parameter and fragmentation velocity for the dust evolution. And you can see that the mid-plane temperature at the very early phase of the disk evolution can be roughly 900 Kelvin at, let's say, 7 AU or something like that. But as time goes, the accretion rate decreases, and the dead zone inner edge moves inward. And because of the MHD disk wind, gas surface density decreases much faster in the inner region. So there is this kind of cavity-like surface density profile can be obtained in the later stage of the disk evolution. And because of this radial migration of dead zone inner edge, the dust pileup can also move inward. So let's say that if the time is 10 to the minus 4 year, the dead zone pileup occur at 2 AU, but this dust pileup moves inward and eventually reaches the radial location 0.1 AU. So this is a rough explanation for the early evolution of the dust pileup at the dead zone inner edge. And if we look at the planetesimal surface density obtained from the dust evolution simulations, we can see that, for example, if the alpha value in the dead zone is 2.3 times 10 to the minus 4, the total mass of 2 Earth mass can be obtained near the 1 AU. So, but on the other hand, the alpha value is slightly higher than this typical value. So let's say 2.5 times 10 to the minus 4. Then total planetary mass, total planetesimal mass is order of 50 Earth masses. So the total planetary mass formed in the dead zone inner edge is very, very sensitive to the alpha value and the dust size. If dust is marginally trapped at the dead zone inner edge, then total mass can be 2 Earth masses, which is comparable to the total mass of the inner solar system. But if the dust trapping is very efficient, so the total mass can be a few tens of Earth masses. So this is more consistent with the super Earth systems in terms of the total mass. And actually, this narrow ring configuration to planetesimal mass is consistent with the prediction from the inner solar system configuration, in which there are 2 large bodies sandwiched by smaller planets. So this is a paper by Hansen 2009 that they proposed that to explain this sandwich configuration, this kind of narrow planetesimal ring is preferable. So this planetesimal distribution naturally explain this inner solar system configuration. And actually this planetesimal formation at the dead zone inner edge may explain the carbon depletion in the Earth. So this figure shows the carbon abundance relative to the silicate as a function of the radial distance from the central star. Not exactly the radial distance, but roughly the radial distance. And you can see that the Earth is very depleted in the carbon relative to the solar value. So this carbon depletion suggests that the building blocks of Earth has experienced temperature higher than 500 Kelvin, so that the refractory carbonaceous solids can evaporate. So maybe this planetesimal formation at the depth of the inner edge can explain the depletion of the carbon in the Earth. Okay, so the rocky planetesimals may form at 1 AU during the earliest phase of disk evolution, but can planets form from them without significant inward migration, because the gas surface density is very high in the earliest phase of the disk evolution, and which means that the type 1 migration is also very efficient. So the question is that the large planets can form without significant migration or not. So the MHD disk wind is very important. If MHD disk wind dominates the disk evolution, this kind of positive surface density gradient can be obtained. This is because basically the MHD disk wind is much more efficient to remove angular momentum at the inner region of the disk, because the Keplerian frequency is much faster in the inner region. So if this kind of positive gradient in the gas surface density is obtained, then we perform the N-body simulation considering the migration based on the planetesimal distribution obtained here. And you can see that there is no significant inward migration for the time of the 100 million years. So eventually we can obtain the planetary system very similar to the inner solar system. So this positive surface density gradient is needed to prevent significant type 1 migration and obtain the inner solar system configuration. And this figure shows the mass semi-major axis distribution obtained from our N-body simulation, 10 N-body simulations. And the red dot shows the inner solar system planet, and the blue dot shows the simulated planet. And you can see that our simulated planets roughly explain the orbital configuration of the inner solar system planet. So in summary, the planetesimal formation at 1 AU at the highly accreting phase of disk evolution can be occurred. And the inner disk clearing by MHD disk wind is a key to prevent the significant inward migration of the planet. And then after 10 million years or something, then gravitational accretion of the protoplanets without significant migration can be explained. And in this simulation, we focus only on the planetesimal formation at the depth zone inner edge, but actually there are another potential sites for the planetesimal formation. For example, the H2O snow line and the CO snow line. This kind of the distinct locations maybe explain the distinct planetesimal population found in our solar system. Actually, Isidoro 2022 explained that this kind of planetesimal formation at 3 distinct pressure bumps can explain the orbital configuration of the solar system. So this is actually very interesting. So, but question is that, as I said, that the planetesimal formation efficiency is very sensitive to the dust trapping efficiency, more specifically the ratio between the Stokes number and the turbulence parameter alpha. So this parameter determines both the efficiency of planetesimal formation and the dust mass flux into the inner region. But how efficient is it in the real disk? So this is the next question. Actually, at least in the outer region, there is a discussion that the dust particles should be very fragile. So this is an example that the left figure shows the simulation of the dust evolution with including the pressure band. And if dust particle is very sticky, I mean the fragmentation velocity above which dust collision results in the fragmentation is very high, then dust particle can grow into very large at the pressure bump, because there is no dust radial drift. The dust particle can just grow into large bodies, right? But if the fragmentation velocity is very low, even at the pressure bump, dust size is limited by the fragmentation, so there is a kind of smooth dust size distribution in the radial direction. And what we found in the real disks, so this figure shows the surface density and the maximum grain size estimated from the multi-wavelength ALMA observation. I think that these figures are too small for you, but anyway, the key point is that if we look at the dust traps, I mean the dust rings in a real disk, we do not observe significant dust size enhancement at the ring locations, which means that the dust size should be regulated by fragmentation. And in this paper, they argue that at least these 7 disks, fragmentation velocity should be order of 1 meter per second or something like that. So dust should be very fragile. And actually, more detailed modeling for the IM loop disk obtained the similar conclusion. So in this study, we try to model the several observations from the millimeter dust continuum observation at 2 wavelengths, and the millimeter polarization at 2 wavelengths, and the near-infrared polarized scattered light mesh. And these disks are known to be very huge and shows this kind of spiral arm structure, and actively studied in the previous studies. So this rich observational data set allows us to infer the dust properties in very detail. So this workshop is focused on the inner region, so I do not explain detail, but point is that, so if we try to explain all these observations in a single self-consistent model, we need very fragile dust particles. So these 2 left panels shows the millimeter Stokes emission at 1 millimeter and 3 millimeter, and the top panel shows the dust with fragile dust model, and the bottom one shows the sticky dust model. And the dotted line shows the model intensity, and the solid line shows the observed intensity profile. And you can clearly see that if the dust fragmentation velocity is 10 meters per second, the model intensity is significantly lower than the observed intensity, because the dust particle can grow larger and drift very quickly. So the disk is depleted in dust particle. But if the dust is less sticky, then the model can explain the intensity profile reasonably. By the way, in this modeling, we do not do any fine tuning, or we do not do fitting. This is a completely forward modeling based on the dust evolution in the gravitationally unstable disk. So I'm actually very surprised that this model can explain the observed intensity profile very well. But if we look at the millimeter polarization at 1.3 millimeter and 0.9 millimeter, this is again that the observed polarization degree can be reasonably explained by the very fragile dust particle. But this is again that if the dust is sticky, there is no observed detectable polarization from the disk. So these 2 observation comparison strongly suggest that the dust particles should be very fragile. And also, if we look at the near-infrared scattered light, and this is an observed image, and the left panel shows the fragile dust model, and the right panel shows the sticky dust model. And this is again that fragile dust model can better explain the observation. This is simply because if dust is fragile, then there are more small grain in the disk, and which is more consistent with the observation. So based on this detailed modeling, so fragmentation velocity less than 1 meter per second is required to consistently explain all these observations. But actually, this might be inconsistent with the gas observation. So as we already have a talk about the JWST observation, and there is a argument that cold water emission, there is an excess in the cold water emission in compact disks. And this may be attributed to the efficient radial drift of icy pebbles. They can supply the water vapor in the inner region. So question is that the open question is that is fragile dust scenario consistent with the gas disk observation like this? Okay, so I want to wrap up the talk but so now, for example, the H2O sublimation line and dead zone inner edge, the location of these are very sensitive to the disk temperature. So, and the disk temperature affects the dust evolution, and dust evolution affects the disk temperature profile because the opacity source is dust in the disks. So we perform the dust evolution coupled with the temperature evolution that accounts for the opacity variation induced by the dust evolution. So we self-consistently calculate the dust evolution with the temperature evolution here. And we found interesting behavior here. So this is a movie that if there is some perturbation in the dust surface density, this kind of perturbation can grow and very peaky dust surface density can be obtained, and eventually the dust to gas mid-plane density ratio can exceed unity because of the feedback from the dust evolution onto the temperature structure. And this can be understood as follows, that if there is some concentration in the dust concentration, there is a small bump in the temperature structure if the disk is actively heated. And then if there is this kind of bump is formed, the dust particle just outside the dust concentration has a higher drift velocity due to the steeper negative temperature gradient. But on the other hand, inside the dust concentration, dust drift is suppressed due to the positive or flat temperature gradient. So there is a kind of instability that the dust particle can concentrate onto the bump-like structure. And this phenomena can happen in the specific condition where the turbulence alpha dust diffusion timescale is longer than the drift timescale, but the drift timescale is longer than the thermal diffusion timescale. But anyway, so this is kind of interesting to form the rocky planetesimals in the inner region of the planet. And yesterday we have a very great talk from the Michael Cecil, and they found that there is a kind of instability in the inner region that pushes the dead zone inner edge much outward. And we are now working on the planetesimal formation in such kind of the bursting phase. So, and this is a very ongoing project. So I don't want to explain about the detail, but thing is that if, this pink region is the MR active region. So the MR active region can happen and then vanishes as time goes. So it's very chaotic, but anyway, there are some interesting physics happen in this region. So I'd like to skip this talk. So, okay, thank you for your attention.
Now session is open to questions and comments on the right.
Ruth Marie Clay, UC Santa Cruz. My question is, for the dust strength, is that degenerate with the amount of turbulence in the disk? Can you tell the difference between the dust being fragile and the dust just being mixed up very well to the surface?
Could you say again that?
Can you tell the difference between the dust being fragile, so there's a lot of small dust, and there being less small dust, but it's mixed well to the surface?
Okay. Yeah, actually, it's a kind of bit difficult, but so you mean that this object?
Yes.
Right? And the point is that so, for example, if we try to explain the infrared scattered light only, then okay, then we can just lift up the small particle in the vertical direction and just ignore the midplane density. That's fine. But if we try to explain the millimeter emission as well, in addition to the scattered light, then we need much more dust particle even in the midplane. So we require both mass and particle distribution. Yeah.
Okay, just Chuck.
You discussed different parameter ranges for formation of super Earths versus the terrestrial planet configuration in our solar system. Do you expect there to be a bimodal distribution of planets, or because there's a tiny range where you get a transition, or do you expect a continuum?
Okay, that's a very good point, I think. But at least we have not yet examined such kind of the demographics obtained from the simulation. But I expect that, yeah, as you say, that this planetesimal distribution with total mass of 2 Earth masses is kind of very rare. So I expect that there is a more kind of bimodal distribution, or this is kind of super rare, at least in this context.
Incidentally, Kepler would have been very lucky to detect a true Venus analog or a true Earth analog. Sorry, thank you, Ichiro. Kepler would have been very lucky to detect a true Venus analog or true Earth analog. Even if they occur around most stars, there isn't a high chance that it would see it. Only the best stars, and it has to line up properly. And Mercury and Mars, pretty much hopeless.
Thank you.
So I have two questions, 2 parts to my question, and one relates to what Jack was just talking about, which is the plots that you were just showing on the sensitivity to alpha of the profiles, the sensitivity, the sensitivity to alpha of the profile. Yes, that one. Yes. Is there also a sensitivity then to the grain size distribution or the fragmentation that you assume?
Yes, yes. So in this simulation, we fix the kind of fragmentation velocity and change the alpha value. But of course, this total mass depends both alpha value and the fragmentation velocity. So yeah.
And also on the fragmentation issue, if you could go, this relates to Ruth's question. If you the result showing the suggestion that the fragmentation velocity has to be low, does that assume where that scattering dust comes from? So in the disk, so you showed this in the question of the low fragmentation velocity that you were deriving based on the profiles for the scattered light from the disk. Yeah, does that matter where the dust is coming from? For example, there is a suggestion that a lot of this dust may be coming from a wind and is thus emanating very close to the star, or much closer to the star, where the velocities are much higher. Could that help explain why you have small grains?
You mean the scattered light?
Yeah. Yeah, you're saying you need fragile dust to explain the small grains. Yeah. But does that matter where the dust is coming from, that interpretation? Could it come from very close to the star and being blown out in a wind that we're seeing?
Yeah, actually, that's a very good point. So there is a study that, at least in this disk, there is a kind of indirect evidence that the small dust particles has a very, how to say, high scale height within 20 AU. Yeah. And so that is a kind of can be origin of this shadow-like structure. So it might be due to such kind of disk wind.
Okay.
Wait.
Yes, Paola Pinilla, UCL. I have a question about the possible degeneracy with the dust opacities in this conclusion, because from my experience, if you change the dust opacity composition, you can enhance the flux, you can change the polarization pattern. So yes, can you please comment on that?
Yeah, it's very great question. Thank you. So, to explain these observations with large fragmentation velocity, one solution is that we assume higher absorption opacity. Let's say that if the absorption opacity is 10 times higher, then Stokes emission can be consistent with observation, right? And it can be achieved if we assume the amorphous carbon-rich dust particle. That is one solution. But if we assume such kind of amorphous carbon-rich dust particle, then scattering polarization is less efficient. So to explain these two Stokes emission and millimeter polarization simultaneously, it is very difficult if we assume the more higher absorption opacity. So that's a kind of issue.
Okay, so first maybe then.
Lee Hartman, so when you have these very low surface densities in the inner disk, have you calculated what the accretion rate would be onto the star?
Accretion rate?
Yeah.
In this?
Accretion onto the star, right? So
you
if you have no surface density, then you would have a very low accretion rate.
You mean this model?
Yeah.
We do not calculate the accretion rate onto the star, but yeah, in this model, we assume that some mass ejection by disk wind. So I expect that the mass accretion rate onto the star can be, can be lower than the typical disk evolution because.
So there are observational constraints on how much. There are observational constraints on how much accretion is. So that might be a thing to check.
Yeah. Thank you.
Yes, Ralph Pudritz of McMaster. In a related question to the last one, presumably that key assumption that you're evacuating the inner disk depends on having disk winds that are comparable to the accretion rate.
Yes.
Disk winds are well known to be very efficient where that ratio would be very small, except in some simulations. So are you just sticking that in by hand, that m dot wind is m dot accretion for your model, or are you calculating something else?
Yeah, we calculate the angular momentum transport by disk wind and also the viscous angular momentum transport proposed by the Suzuki et al. 2016. So it's a more, at least within this model, we calculate the self-consistent disk evolution. But we do not check the accretion rate onto the star. So yeah, that's a good point.
Okay.
So along with Ralph's question, I mean, if you're really ejecting so much stuff, then it means that the magnetic lever arm
is one.
Yeah, yeah. So and then the wind would be relatively slow.
Yeah.
And so maybe that's inconsistent with wind velocities that we see from the inner disk.
Hi, Steve Dash, Arizona State. Picking up on the same theme, in my models, I also found a positively increasing surface density as you went outward, doing an alpha that increased as you went inward and decreased sharply. And I was trying to mimic exactly the Suzuki et al. 2016. So I would say it's not so much that the wind is removing mass, it's just that it's leading to a very high alpha, which kind of shoves the mass you have in the disk out. Is that an okay interpretation?
Yeah, so I do not check the exact ratio of the mass accretion rate onto the star and the mass loss by the disk wind. So I cannot answer to your question, but I should check that. Yeah, thank you.
Okay, still a few minutes. Any questions? So then I have one. So if the fragmentation velocity should be less than 1 meter per second, can you still make pebbles?
Yeah, so that is something I want to ask you in this workshop. So there is so in this morning, so Sheila Grant's talk, so there is a kind of indirect evidence of the radial migration of dust particles. So yeah, even dust is very fragile. There is some level of the dust drift. But my point is that how much is the radial pebble flux and how much the pebble flux can continue in the whole disk evolution, right? So, and I think at least for now, we do not have a clear answer to the such kind of the values. So that is something I want to discuss.
Okay. Any comments? Okay.
If I can comment on that question, I would say the answer is yes, that we can form pebbles, and I think it's good that they are these fragmentation velocities because you have a lot of small grains that can leak through these gaps and explain all of these conversations as we are talking about JWST. So I think this all goes in a good agreement.
Okay, thank you for the comment. So any other questions or comments? Okay, Jack.
No other question. I'll just comment on the history of this. Safronoff and Goldreich, somewhat independently, performed analysis of the gravitational instability, and then Weinschelling showed that there was the turbulence, so it wouldn't be enough, and you had this centimeter-sized barrier. And people have done all sorts of things with pebbles, et cetera, to try and get around that problem. But I think the most solid new thing is that there's a problem even smaller size in terms of the dust sticking, which was assumed by electrostatic forces, but now that there are better calculations, et cetera, like this and some of the things we see in the posters, the problem has gotten to be broader. Well, it's a smaller size, but it's extended. It hasn't gotten rid of the problem at the centimeter size.
Okay, the last, yeah.
Okay, thanks. Steve Dash again. Yeah, I think when we talk pebbles, I think we have in our minds that they're centimeter or larger size things, but we don't have those in meteorites. We have chondrules. They're millimeter size. Those are the pebbles. They're not going to be limited by the fragmentation barrier. I think the bouncing barrier is probably it. And that's what we should think of as pebbles. It's not a feature. It's not a bug. It's a feature.
I see. Okay, thank you for the comments. So let's thank Takahiro again.